Good afternoon, everyone. We are Group 5. We're going to be doing our presentation on structural engineering and finite element analysis using daily decomposition. So, me, myself, are modifiers, Jubin, Erika, and Miran. So, first, let's go through what is structural engineering. So, structural engineering is basically all about making sure when you build a structure, like a building or bridge, you need to make sure it's stable and it's strong. So it focuses on ensuring that buildings, bridges, dams, and other structures are safe. Because if we didn't do this, we're gonna make weak structures in real life. So it makes sure that the structures can handle weight, weather, and movement, physical weight, and weather and movement. And what's FEA? FEA is basically finite element analysis. It's it helps perform structural analysis by breaking down the structure into smaller, manageable parts. Basically, when we want to see how a building reacts to a physical force like wind or earthquake, we can apply the finite element analysis. We make the structure into pieces, and we do the finite element analysis on each and every piece, basically. Now I'm gonna be giving the mic to Milan.
So for finite element analysis, we are actually dividing the structure into finite elements like here, as you see. The bridge is divided into different structures like bearing, beams, deck, etc. So in order to do FEA, we will have to have an understanding about the stiffness matrix. So basically, a stiffness matrix tells us the resistance of a structure or a material towards deformation under applied forces. So it is a critical component in FEA of structures such as bridges. So for a structure like a beam, the Euler-Bernoulli theorem can be used to derive the stiffness matrix. So in order to understand what a stiffness matrix is, we'll have to have an understanding of what are knots. So knots are key locations or points in a structure which is used to define the whole structure and used for calculations. So So all these diagonal entries in the stiffness matrix represents the self-stiffness or the self-resistance of knots, the force values which is required for the self-resistance. So all the non-diagonal entries are basically the force required that is to be given to a node 1, which causes a unit displacement in node 2, and similarly all other components. So our approach is to use the stiffness matrix and decompose it into a lower triangular and upper triangular matrix and solve the equation and form a displacement vector which tells us how much the nodes will displace under different loads. So Jubin will lead with an example.
So good afternoon, everyone. So I think all of you got what is finite element analysis, and it is dividing the suppose part of which something buildings or engineering structure into some parts and analyzing what amount of load stress and all happens affect the portion. So we are using LU decomposition method as mentioned by Milan. So I'm here going to explain what briefly not mathematically about how can LU decomposition can be applied to this finite element analysis. So as we all know, we studied that what is LU decomposition, right? So we can write as suppose if there is a matrix A and what like this. So we can write as we can decompose this matrix as A is equal to LU. That means a product of lower triangular matrix and an upper triangular matrix. So similarly, we have in this in this finite element analysis we have matrix K. K, that means this matrix is known as stiffness matrix. And if there is another vector F, that means force acting on the structure. So the force acting on the structure. So likewise in this A is equal to LU part, we can multiply as Kx is equal to F. That means K is a stiffness matrix and it is multiplied by X. X means the components of the nodes at the nodes. The displacement is equal to F. That's a force vector. That means if a force is applied or on a bridge or any structure, that is the force F. That's also a vector. So whiteboard. Okay, so we have Kx is equal to F and K is equal to LU. That means decomposed by lower triangle and upper triangle. So we can write it as LUX is equal to F. So therefore Ly is equal to F. That means that is Y is equal to UX. We can write it. So then similarly, like we studied on solving this equation, finally we get the X values. That means the displacement happens on each side. So I'll just explain a mathematical problem of this. And suppose we have a L lower triangular matrix like 1, 0, 0. And minus 0.25, 1, 0, 0, minus 0.267, 1. This was lower triangular matrix, and upper triangular matrix was 4, minus 1, 0, 0, 3.75, minus 1, 0, 0, 2.73. So this was the two matrix, and we are we have what we need to find Y. That means So also we have stiffness matrix K is equal to 4, -1, 0, -1, 4, -1, 0, -1, 3. So applying the method, okay, Ly is equal to F, which implies L is given as 1, 0, 0, minus 0.25, 1, 0, then 0, minus 0.267, 1, into y. Y means y1, y2, y3 that we assume is equal to a force vector that is 10, 20, and 15. That is, we are applying force on 3 directions. That means it is a vector. So each direction, fx, xy, it is 3 components of a vector resolved at the node. Node means the point of force acting. So on solving, we get y1 is equal to 10, then y2 equals 22.5, then y3 approximately equals to 21.01. That means the 3 components of y. Then with this y, we can solve, we can find the x. That means ux is equal to y. By substituting this y on this matrix, that means the matrix we have u, upper triangle matrix. So we have u like this, 4, -1, 0, then 0, 3.75, -1, 0, 0, 2.73 into x. That means x1, x2, and x3 is equal to the matrix that we get 10, 22.5, 21.01. Then so on solving, we get x3, similarly like previously we solved, x3 is equal to 21.01, x2 is equal to approximately equal to 8.05, and x1 is equal to x1 approximately equal to 4.51. So this was the 3 components of x. That means the displacement acting on the bridge. That means these are 3 components of displacement. So that means x in I direction, x in xi, xy, xj, like that 3 components. So this is also a vector 21.01, 8.05, and 4.51. So this was the main use of application of value decomposition. And by this, we can find the displacement occurred by acting a force F on a bridge or any structure. So this much displacement happens on each direction. So next, I hand over mic to Devika.
Hello, I'm Devika. Discuss about the Python code used for solving structural analysis problem using value decomposition. So, as mentioned earlier, our formula is Kx is equal to F, where K is the stiffness matrix. That means the resistance of each point to the deformation, and FEC force applied to various points, and XEC displacement happening to each point due to the applied forces. And there is another matrix called permutation matrix, which accounts for the uh, matrix during decomposition. So coming to the code, we use two libraries in Python, that is NumPy and SciPy. First of all, we want to perform this by doing three steps. First of all, we want to decompose the stiffness matrix into L, U, and P. Then we want to find the Y, the intermediate matrix, and at last we want to find the displacement vector X. So first, we should define the stiffness matrix and force vector by K is equal to NP array and giving the matrix, and F is equal to NP dot array and giving the force vector. Then we want to decompose this stiffness matrix K into LU and P by the LU type-wise LU function by in PLU is equal to LU of K. Then we want to print that L and U matrices, and then we want to find the intermediate matrix Y. For this, we use the code np.linear.solve of L comma np dot P and F. So also then we get the intermediate matrix, and at last we want the displacement vector X. For this, we want to do np.linear.solve U and Y. Then we get the displacement vector. By analyzing if the displacement vector is large or small, we can know that the strength of buildings, bridges, or something like that. See, output is given here.
So I would like to explain about the advantages of using LU over other methods. Like we have other decomposition methods like SVD. SVD requires decomposition into three matrices in a scenario where we require less computational power and less memory. LU decomposition is much more faster and efficient. So it makes it faster than SVD because only two types of steps are involved, which is forward substitution and forward and backward substitution. Next, we have the memory efficiency for sparse matrices. Most of the entries in the stiffness matrix might be zero. So while handling sparse matrices, LU decomposition is much more memory efficient. And to elaborate more on the topic, we have reusability. That is, both the lower and upper triangular matrices can be reused a number of times for different load scenarios. That's all. Thank you. Sir, if the stiffness matrix is large or the structure is huge, we require lots of computational power. So we only demonstrated it in a 3x3 matrix, but actually in real case scenario, the stiffness matrix is really huge. So the computation is required. Stiffness. Yeah. Stiffness matrix. This one. Yeah, only for square matrices. Yes. It means that the force that is exerted on is in the opposite direction. Yeah. How does it
Yeah, the vector it means the size of the matrix A like I want to see like what it is 40 square matrix.
Elements മാത്രം മനസ്സിലാണോ മനസ്സിലായില്ലേ മനസ്സിലായി ഒരു റോ അല്ലേ കഴിഞ്ഞോ
It is really cool the application. And before saying it out, can you give me two examples of this structural one really cool application which has a natural calendar.
constructing
Yes, but they are natural calamity like all quick.
Hmm.
So it building like a building you right like think of this apartment in this scenario like as a trees. Yes, how one block is connected to another block and another block. Right? So how those were connected. So even in my apartment, if someone in the morning someone makes tea, the ginger bit used to spice it up. Even though I can hear it. Okay. So therefore, yeah, this is what so therefore, what I meant to say is they are interconnected. They are all one my position floor will be connected to someone else. Okay, so it is coupled system. And to say that it's coupled, you can either be connected with things. Just you can model it. If you want to model it.